all do this, right? Question 1, question 2, question 3, question 4, that's okay, right? Question 1 says rank the pKa's of an acyl chloride, ester, amide, or ketone, and ketone. From most to least, there's a variety of orders here. Everything is discerned a letter, right? The second question says, which molecule has the most stable conjugate base? Okay? Second. The third one says, what is the acid-base reaction analysis is for what transformation? That's what AB is, acid-base. The acid-base analysis that's shown is for what transformation? Some choices here. And what are the synthetic steps to convert ethyl butanoate to butanoic, propanoic, anhydride? Okay? If you can't read something, raise your hand. I'm happy to interpret my scroll. Yes?
The last part of the acid-base reaction on sentence 3, is that
KOC in parentheses O. Everyone know what that means? That means the carbonyl, right? That's how we write a carbonyl. If I put in the carbonyl, it would have had to go into the words. So. Yeah. Most acidic to least acidic. So the most acidic molecule should be on your left, right? And the least acidic should be on your right in those orderings. Okay? That was your question, Mickey, because you were nodding. Okay. All right. Let me get out of the way then. We'll put about 4 minutes on the clock here, 5 minutes on the clock. If you have questions, you can raise your hand up.
Are you saying this would be the most stable? This is the most stable?
Yeah, because there's no options. They're more like with the first one.
Okay, so we're going most stable to least stable. So, wait, but acyl chloride is the last one.
Conjugate bases are never last. Okay,
So would it not be reactive to just aldehydes? Yeah. No, most reactive, most stable. Because they want to get like more willing to get there, so they have a stable base. So you're saying 1? Acyl chloride is A. Oh, acyl chloride is A. Yeah.
also acyl chloride.
Ketone, they're saying is D.
Because like for the ester,
It's even more. Yeah. I
so
see.
that should be the least.
I think it's
So I started with the lowest. What about the chloride? I would think it would be so chloride. What is it? Down. Daniel said depropane and then look at from resident's point of view.
I just thought would be 5.
Okay.
So this one is
H.
that would have all of it. So
Yeah.
right. So and then where hopefully that'd be awesome.
Fourth. Because I think acyl chloride. Okay. Because the first one says acyl chloride is the least. Or it has the lowest. Oh, it has the lowest concentration. Lowest pKa means the most stable gas.
Of the hour to the top of the hour. Anyway, on Marketplace, they were talking about this story about one study says that drinking coffee in the morning is actually good for productivity. It actually wakes your mind up, right? Allows you to sort of be all in, be on top of your game, the whole 9 yards, right? So they say that's great, and I believe that. The follow-up study, though, says that when the caffeine wears off later in the day, your productivity goes way down. And that's when they find that a lot of workers start to cheat and lie and do all of these different things, right? So as he's closing out this story, I don't even know who the announcer is, but as he's closing out this story, he says something like, so you start your day as an earnest chemist, and you wind up as Walter White. So I thought that was really funny. So here I am in my semi-earnest mode, right? And I'm going to go home and I don't even know, right? Make methamphetamines, I guess. I thought that was highly entertaining. Okay. We should have all the clicker questions in at this point. If you just toss them up here. If you didn't hand it in, just toss them up. Is that yours? Oh, okay, just
Yeah,
okay. Thanks, Kim. Okay, so let's start and make sure that we can do these problems. So this is the first problem that I promised, right? And that is the acyl chloride, ester, amide sort of thing. Now, Daniel asked a very good question, and that was, what proton are we talking about? So the first thing you always want to look at in a molecule is, what is the most acidic proton? Remember, every proton in the molecule has a pKa. And whenever we're looking at a molecule, we're always thinking of the lowest pKa first. That's what we're coming to, right? So when I look at all of these molecules, an acyl chloride, so we can say an acyl chloride, which is A, we're looking at this proton. When I'm looking at an ester, I'm likely looking at this alpha proton as well, right? So A, B. When I'm looking at an amide, though, unless it's dimethylated, I am looking at this proton here. Okay? The most acidic proton in an amide is off the nitrogen. Why is that? That's right, because the conjugate base is more stable. That's what we are always looking at, right? We're always looking at stability of the conjugate base. A more stable conjugate base is derived from a stronger acid. So the four things that we look at with this stability of the conjugate base include the electronegativity of the atom, size, resonance, and hybridization, right? That goes all the way back to Gen Chem. So again, electronegativity of the atom, size, resonance, and hybridization. So nitrogen, right, sitting where it is, has one thing, but it also has the associated resonance with it. This is actually the most acidic. Very, very odd, but true. Okay, and lastly, the ketone also is looking at the alpha carbon as well. Okay, so now we have to begin to order them, and this is where we have to begin to know our numbers. Okay, this is probably the one that might have thrown you out of whack. This guy is 15. Okay. This ketone we've talked about a lot, so that's 16 to 20, so obviously this is less acidic than that, right? Does anyone know the ester? This one I wasn't sure you'd all know, which is why I gave it to you. This one, though, we knew from class. Ester, we have talked about a couple times. Does anyone know what the pK of this guy is? 25, great, so this guy's 25. Does anyone want to take a guess at an acyl chloride?
8.
Lower?
8. 5.
Yeah, it's in the low teens. But certainly it's going to be lower than my ketone, my ester, etc. So in order then, for most acidic, A is the most acidic. So we're going to knock off 1 and 5. So A is the most acidic. Followed then by, where am I here? Probably C, right? Okay, well then that knocks these off here as well. So now we're here.
Can we do an approximate pKa for A?
I would guess it's probably about 10 to 12. Okay? That'd be my guess. Yes. That's a great question, Daniel, again, with a really good question. Let me answer that question for you. What would the pKa be saying if this wasn't hydrogens out here? So let's say I make a methyl group here, and I have a methyl group here, right? Then I don't have a hydrogen off the nitrogen anymore. So it's not 15 anymore. So now we have to begin to look at the alpha carbon. So in this case, this guy would be 30. Okay? So when you have two R groups off the nitrogen, and therefore no hydrogen off the nitrogen of an amide, it gets to 30. Does everyone understand? It follows exactly that table. Does everyone understand what I mean? It's exactly following that table that we've talked about. The acyl chloride has the most acidic pKa at the alpha site. You would expect the anhydride to be next, followed then by the ester, and finally the amide. All's following the table. It all goes back to resonance arguments. This is your third example of a resonance argument. So if you don't study accordingly, then you're going to be considered not an astute student. Ready? Number 1, we talked about the reactivity, right? The reactivity order based on the table, all resonance related. 2, we've already talked about the carbonyl bond strength, all resonance related. And number 3, the pKa's of these alpha protons, all resonance related. You need to be able to make a resonance argument for one of those 3 categories. You will see it on your test. Okay, so you are going to be reporting back to me what the argument is. For instance, why is the acyl chloride more at the alpha site more acidic than an amide? You're going to give me this back with a resonance argument, with resonance structures drawn and an understanding of contribution to the resonance hybrid as we've talked about. Alternatively, what's more reactive, an ester or an anhydride? And why? You say an anhydride because of the resonance argument. You give me the resonance argument back, contributions to the resonance hybrid, and explanation from there. Okay? Does everyone understand what I'm saying? Everyone feel that they could do that?
So reactivities and pKa's do or do not always correlate?
They generally do, actually, surprisingly, because they're all centered in that same area, right? Not globally in different areas of the molecule, but they're all centered in that area. Yes, they do. They're all going to ride around that resonance argument. Okay, are there any more questions about this? Yeah?
What's that? You said what was the first argument before the carbonyl strength and the pKa?
So we have carbonyl strength in terms of the strength of the carbonyl bond, the pKa, and then the reactivity, meaning the reactivity of the carbonyl carbon, right? Which functional group is more reactive? Okay, no more questions about clicker? Yes? What?
Is it because it's not 2 because the nitrogen is not 2 methyl group?
Yes, it's 2 because the nitrogen did not have 2 methyl groups on it.
So
Yes.
it is that it's
Correct. Yes. Yes. Okay. All right. Okay, so the second question says, which one of these conjugate bases is more stable? Does anyone know what we're going after here? What is this talking about?
the electron donating.
It's talking about electron donating groups. It's talking about carbanion stability. Carbanion stability. That's really what it's talking about. Okay? So if I look just here, so if I look, say, at the conjugate base here, there is no conjugate base for C, by the way, right? There's no, well, I mean, I guess you could put one further out, but that wouldn't be the most acidic. And you look, say, for this guy, okay, I've just drawn up 2 potential conjugate bases. Hopefully we're making conjugate bases at the alpha site. We do not want to make them further away from the alpha site because the pK is going to come and ride towards 60, right? They're only lower when they're down next to the carbonyl because of the resonance argument, okay? So this is all about carbanion strength. I'm reticent to say this, but you should have learned this in OChem 1. Does anyone know which carbanion is more stable? The one on the right or the one on the left?
Right.
Okay, this one's more stable. It's something that comes out in Orgo 1. Just in case you didn't know, I'm here to tell you, I'm here to remind you now. Carbanion strength goes opposite to carbocation strength. Okay? Remember that all these R groups are electron donating. And when you donate electron density toward a negative charge, that destabilizes the negative charge. Right? So, the carbanion on the right is more stable because it doesn't have extra R groups donating electron density toward it. Okay? Someone asked this question at the end of class last time, and I said I was going to come out with a clicker question to remind you, or to teach you, lest you didn't know. Okay? Everyone understand this clicker question? Yeah? Yes, I can. So I said that carbanion strength goes opposite to carbocation strength because all of these R groups are electron donating. And if you donate electron density toward a negative charge, right, you're going to destabilize that negative charge. Okay? So In terms of looking at that carbanion itself, right? If more R groups is worse. Therefore, we know the guy on the right is more stable, and that was derived from A. Okay? Yes?
So we're always going to want to have the negative charge next to that because the other the hydrogen on the terminal.
Okay. This is a great question because this is gonna. How many of you guys are gonna go into biochem eventually? Because this is really gonna rot. This really is where the rot begins. We have such trouble with this in biochem when we teach it. So when I look at this molecule, there are a bunch of different pKa's. There's this, whose pKa is 16 to 20, and then anything out here, right, has a pKa of 60. In essence, this does have two different acidic environments, right? One's going to be abstracted first, and one would require something off the chart to abstract it. But certainly if I had something, right, I can push deprotonation out there as well. So whenever you look at a molecule, you always have to center in first toward those electronegative atoms, right? You can't have it off of an electronegative atom. You want to soak to, or you want to, next spot is to those resonance locations, right, which are alpha to the carbonyl. Okay? Questions about that? Yeah. So in this case, this guy is probably going to ride more toward 16, right? Whereas this one over here is probably going to ride more toward 20. Thanks for bringing the lesson back around, Dan. I appreciate that, because that is actually the readout from this, right? The idea is there's a range, right? There's a range, 16 to 20. 16 is something that's more acidic, in essence, then, has a more stable conjugate base. So what I would expect is that the proton here off the alpha carbon is more acidic, rides more toward 16, and this guy is more toward 20 because the carbanion that's created is less stable. Okay? And C doesn't even have a proton off of that, it's at 60, right? Yeah, because there's no proton off the alpha site. Yes?
What if there was just one methyl group?
So if there's...
An alpha hydrogen to the left of the carbonyl, would it that?
So I love when you guys want to change them up. So you want just to have this. This guy? You just wanted one methyl group. So there you go. That's an aldehyde though. You want this one?
I mean,
No?
like on the molecule on the left, see how there's two methyls hanging off. What if there's just one methyl?
So in this, okay, I see your question. Okay, so the question is, which of these is more, this brings up some actually really interesting stuff that we'll be talking about more. So the question is, which one of these, right? This one here is going to be easier to pull, leading to the more stable conjugate, right, base, right? But the problem is there's a resonance argument here as well. Can anyone see it? This is a kinetic thermodynamic argument. Can anyone see? You should be able to see. You should be able to jump there and see with me why there's a kinetic thermodynamic argument here. Look at each of the conjugate bases. So we've talked about why one is more stable, right? So now I have this guy that's pulling this proton here. So that's here. Or I can pull this guy out here, and I get to this one here. Okay? These are the conjugate base arguments. This is the one that I'm trying to make right now. Okay? I'm saying that the triangulated one here is more stable because it's less substituted. But what's the corresponding thermodynamic argument that can be made? Forming a more stable alkene. That's always what it is, right? When you look now at the resonance structures for this, you see that this here forms a more stable alkene than this, right? So this is what we call a thermodynamic enolate. This one is called, over here, it's called my kinetic enolate. You know this comes from direct readout of the stability of the charge left, which in this case is a negative charge, compared with the resonance structure of that direct result. Okay? Does everyone see what I mean by this? Questions about that?
What's the take-home lesson?
What's the take-home lesson here? The take-home lesson is that you can choose either a kinetic or a choose one way experimentally that you can choose one enolase over the other. Temperature. That's exactly right. If I run this at low temperature, am I going to pull the one that's triangulated or circled? And if I ran this at room temperature, I'd pull. Okay, this is exactly the readout, and this is what we see when we do reactions at these sites, which actually is the next chapter here. 1, 2, 3, or 4?
3.
2. The acid-base analysis is always between the leaving group and the protonated nucleophile. Okay? So this is obviously the protonase analysis. I know the acid-base analysis is always between the leaving group, which has a negative charge, so I'm looking for something with a negative, right? And the protonated nucleophile, which should always be some electronegative atom, right, with a positive charge on it. So I know this is the protonated nucleophile, and I know this is the leaving group. The leaving group tells me what functional group I started with. If this was a Cl-, I would have started with an acyl chloride. If this was an OR-, I would have started with an ester. But this is actually a carboxylate, so I started with an acid anhydride. Now I look what I'm adding. I'm adding an amine. I know to convert from any of those functionalities above it in the table to an amide, I add an amine. That is what I add to convert to an amide. So I know that I started with an acid anhydride from the leaving group, and I know I'm converting it to an amide based on the nucleophile that I'm adding. Would I use excess or not? I would use excess. Make sure you know that you would use excess and why you would need to use excess. Okay? Because you're all astute. You're all paying very close attention. Are there questions about this? Yeah.
Do you need excess because the O- isn't gonna, is it like protein fat?
Very good. The reason you need excess is because the acid-base reaction here sits to the left, which in essence means I can't use all of my amine I'm adding as a nucleophile. Some is being used as a base, and therefore not used as a nucleophile. Now that doesn't mean some conversion isn't going to happen, right? But you certainly aren't going to expect 100% yield at all. At best here, you're at like 50%, roughly. Okay? You'd have to do the calculation, the equilibrium calculation, etc. But you can figure that out. You won't be asked to on a test. I'm just saying you could figure it out. Okay? Are there any more questions about this clicker question? Okay, so this is the last part of the workshops that we were talking about, and then when we're done with this clicker question, I'm going to ask if there are questions about the workshop. Maybe we'll review that for a minute before we move on. But this is the last type of question from the workshop. This is asking you to convert an ester into an anhydride. So it's asking you to move up the table. Can you ever move up the table in one single step? No. So that means that these two are out, okay? You can never move up the table in a single step. So what do you need to do? What is the strategy that we employ? Go back to a carboxylic acid. So that requires first hydrolysis. What's going to be your best and therefore full credit hydrolysis mechanism on an exam? Base or acid? I'm going with base. Why is base your absolute best hydrolysis mechanism for an ester, and why would you get full credit? Because it's irreversible. Ding, 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 ding. We call that saponification. Okay? You can move down my chart. Does everyone understand what I mean by this? Okay? There's going to be a couple more questions on the weekly quiz, and they're at the back end of the workshop. The answers are coming out. Make sure you can do those. Okay? And I'll see you guys on Friday.